Hi, welcome to Lesson 3 on Gates and Circuits. My name is Dr. Ritesh Ajoodha. At the end of this lesson, you should be able to solve a few homework problems from Lesson 1 and 2, design a half-subtractor and full-subtractor, and finally, describe the properties of the SR latch. In homework problem 1.3, I asked you to construct the AND and OR gates using transistors. Recall that the basic property of the transistor is that if you put in a 0, you would get out a 1. And if you put in a 1, you will get out a 0. This resembles a NOT gate, so we just need one transistor to implement a NOT gate. To construct an AND gate, recall that if we wanted a NAND gate, we would need only connect two transistors in series. If we do this, then our A and B will output A NAND B. In order to convert this NAND gate into an AND gate, we need only add a NOT gate to the end of it. And the NOT gate is represented by one transistor. So this is the transistor diagram for an AND gate. For the OR gate, recall that to implement a NOR gate, we need to connect two transistors in parallel. If we add a NOT at the end of this NOR gate, we will get an OR gate. This is how we can construct the OR gate using three transistors. In homework problem 1.4, I asked you for the minimum number of transistors needed to implement an exclusive OR gate. Well, let's look at the definition for the exclusive OR gate. From the previous lessons, you found that the exclusive OR gate can be represented by the Boolean expression A0 B or A B0. If we use this Boolean expression for the exclusive OR gate, we can implement it using 6 transistors for the two AND gates, 3 transistors for the OR gate, and 2 transistors for the NOT gates. So we would need 11 transistors in total. This is no longer a problem of simplifying the expression, but rather we need to transform this expression into another expression that uses less transistors to implement it. From the previous slides, you saw that NANDs and NORs use less transistors than ANDs and ORs. So if we can get this expression into a form of NANDs or NORs, then we would use less transistors to implement it. So let's now try to transform this expression into one that uses NANDs and NOR gates so that we can use less transistors to implement it. Well, the way it stands, we have A0 B or A B0. We can add an identity to the second part of the term, A0. And by doing so, this allows us to pull out a common factor A, which might leave us with a NAND gate. Let's see if we can achieve this. So we pull out A using the distributive law, and then we see that we have a NAND gate here, but only after applying De Morgan. We can do the same thing on the other side of the expression. We can introduce the identity B and B0, pull out B as a common factor, and then we have B and A0, another NAND gate. Recall what we did in lesson 2, where we used a substitution term for identical expressions within our larger expression. And we see here that B and A0, this NAND gate, appears twice. So maybe if we use the substitution rule like we did before, we might be able to simplify this further. So let K is equal to B and A0. Then we have the expression BK plus AK. We can use distributivity. So let's pull out K as a common factor, and we'll be left with K into B or A. But K is equal to B and A0. So we can substitute that term back in. And we see that this new expression uses 8 transistors. Since this part of the expression can be implemented using 2 transistors, the AND gate between these two terms can be implemented using 3 transistors, and this OR gate can be represented using 3 transistors. And so in total we have 8 transistors as opposed to 11 transistors as before. In homework problem 2.2, I asked you to prove this expression. That is, I asked you to prove that the left-hand side, A or B and B or C, is equal to the right-hand side, B or AC. You could do this starting from any side you wish. Let's do it from both sides. Let's start from the left-hand side. From the left-hand side, we have A or B and B or C. Using the distributive law, we get AB or AC or BB or BC. We see that the term BB gives us B, and you can prove this using a truth table. So B and B is equal to B. That gives us the expression AB or AC or B or BC. Using absorption, we can absorb this term into a B. Then we can do the same thing on the other side of the expression if we move B as the first item in the expression. So let's use the commutativity law to move B to the beginning of the expression, and also use the commutativity law on this A and B to give us B and A, so that we can use absorption again. So using commutativity, we can move our B to the beginning and swap this term. Now we see absorption can help us again. We can absorb this term into B, and we're left with B or AC. If we approach this from the right-hand side, then we'll get our right-hand side is equal to B or AC. Using distributivity, we get B or A and B or C. And finally, using commutativity to just switch this term, we get A or B and B or C, which is equal to our left-hand side. In homework problem 2.3, I asked you to design a half-subtractor and a full-subtractor, following the half-adder and full-adder example from lesson 2. Well, suppose we want to subtract two digits in binary. Then we could have four cases. 0 minus 0, which gives us a 0. 0 minus 1, which requires us to borrow from the next column. If we borrow, then we'll get a 2. And this 2 units will allow us to subtract this 1 unit. Notice that if you are borrowing in base 3, you would borrow 3 units. If you are borrowing in base 10, you would borrow 10 units, and so on. So 0 minus 1 before the borrow becomes 2 minus 1 after the borrow. So 2 minus 1 is 1. 1 minus 0 is 1. And finally, 1 minus 1 is 0. Notice that this is the only case where we require the borrow. We can now populate this table similarly to the way we populated the half-adder table. Now that we have this table, we can analyze it. So, looking at this column, we see that it's very similar to our half-adder table, where A minus B actually it can be represented with an exclusive OR gate. That leaves us to represent the borrow. Well, using the disjunctive normal form algorithm in lesson 2, we can deduce that the borrow will be true when A is off and B is on. So, all we need to do is design a circuit that, when given two inputs A and B, A first goes in a NOT gate before meeting B in the AND gate to give us A NOT and B. Putting these two circuits together, we get, for input A and B, A goes into a NOT gate and meets B in an AND gate to give us the borrow. A goes into an exclusive OR gate with B to give us A minus B. So this is how we get the half-subtractor. For the full-subtractor, we will have to consider the case where we borrow out to another column who requires the borrow in. To demonstrate this, consider the following subtraction, where we have 10 minus 01. In this subtraction, the first column that we need to conduct the subtraction on is this column. We would start off by saying 0 minus 1. Unfortunately, we cannot carry this out because we need the top number to be greater than or equal to the bottom number. In this case, 0 minus 1 cannot be computed without a borrow. So we require a borrow in from the next column, which will be a borrow out in this column, since this will be borrowing out of its column into this column. If this column borrows out to give it to this column, then this column will now add 2 units to its A and then perform the subtraction. So let's do this. Since we cannot compute 0 minus 1, we will borrow into this column and out of this column a 2. So it becomes 2 minus 1, which is 1. Because there was a b out in this column, we now have 0 minus 0, which gives us 0. Note the context of the borrow in both columns. Let's consider the first row. We have a minus b, and since there was no borrow from this subtraction, we can just say a minus b. That gives us a 0 with no borrow required from any other column. In the second row, we have 0 minus 0, and it turned out that in this subtraction, we did give a borrow to another column. So we need to subtract it as well. However, we can't subtract it without getting a borrow from a different column. So we require a borrow, which allows us to say 2 minus 0, which is 2, and 2 minus 1 is 1. So we will have a minus b as 1. In the third row, a, which is 0, minus b requires a borrow, so we take a borrow from the column next door, which gives us 2 minus 1, which is 1, and then 1 minus 0 is 1. In this column, we require a borrow before we can even do the a minus b subtraction, so we indicate that we need a borrow from another column as a b in, and this becomes 2 minus 1, which is 1, and 1 minus 1, which is 0. And we indicate a minus b as 0. In this column, we have 1 minus 0, which is 1 without any borrow required. 1 minus 0 gives us 1. 1 minus 1 gives us 0 without any borrow required. 1 minus 1 is 0. 0 minus 0 is 0 without any borrow required. And finally, 1 minus 1 is 0. And we require a borrow, b in, to compute 2 minus 1, which gives us 1. Note that in this case, a borrow was taken into another column. And so was the case in this row, and this row. Now that we have the truth table for the full subtractor, we can simply use the disjunctive normal form algorithm on the a minus b column and the b in column and simplify the resulting Boolean expression so that we can construct a circuit diagram. If we use the disjunctive normal form algorithm on a minus b, we'll get the following expression. The steps to simplify this expression into a exclusive or b out follow the same steps that we followed when building the full adder. So I'll leave you to go through these steps on your own, and if you get stuck, go back to lesson 2 to see how we've done this. If you use the disjunctive normal form algorithm on the b in output column, you'll get the following Boolean expression. The first thing we can do to this expression is pull out b out from the first two terms. Thereafter, we noticed that the expression in the parenthesis is actually a exclusive or b not. So we can substitute that in. In the next two terms, we notice that there is an a not b that is common in those two terms, and we can pull that out using the distributive law. We notice b out not or b out can be simplified further using the complements property. The complement property will leave us with the expression a not and b and 1. The identity property can then be used to remove this 1, which finally gives us b out, a exclusive or b not, or a not b. Putting the expression for a minus b and b in together, we can now build our full subtractor by following the logic inside of each of the Boolean expressions. I've done this for you in the following diagram. See if you can construct this yourself. Notice that the full subtractor is made up of two half subtractors. Recall from lesson 2 that there are two types of circuits: combinational circuits, where we have a direct functional relationship between the input and output, and sequential circuits, where the output is a function of the input values as well as the current state of the circuit. In sequential circuits, we can also have your output of the circuit going back as input into the circuit. Circuits can be used to manipulate bits, and also they could be used to store bits. An SR latch is an example of a sequential circuit that can be used to store binary digits. The SR latch that we will be considering in this lesson uses a NOR gate to store a binary digit. Let's see how the SR latch accomplishes this task of storing a binary digit. Suppose we have the following circuit, where S is an input, and R is an input, Y is an output, and X is an output. Then, if S is equal to 1, can we deduce what Y would be? Well, looking at our truth table for a NOR gate, if S is 1, it doesn't matter what value the other input takes. No matter what the other input will be, your output for the NOR gate will be 0. So that means that Y will be 0. If Y is 0 and R is 0, then X would be 1, as indicated in this truth table for the NOR gate. We see that if S is 1, then X is 1. So S being set to 1 allows us to store a 1 inside of X. Let's see what happens when we make S 0. When both inputs are 0, we call this the rest state of the circuit. And we notice that even if S is equal to 0, X still maintains a 1. Consider the case where R is 1. If R is 1, then no matter what the other input value will be, X would be a 0. If X is 0, then this NOR gate will output a 1 as the first row in the truth table. That means if R is 1, then Y will be 1 and X will be 0. A very important property of the SR latch is that Y and X are always complements. That is, Y and X can never take the same value. If we then move back to the rest state, while R is equal to 1, we see that Y maintains being equal to 1 and X maintains its value as 0. There's a state in the SR latch which we just don't use, and we call this the forbidden state. It is the state where S is equal to 1 and R is equal to 1. Consider what happens when S is equal to 1 and R is equal to 1. Well, if we consider the forbidden state, then we can deduce that the output of this NOR gate will be a 0, since the truth table suggests that no matter what the other output will be, even though we don't know what it is, the output will still be a 0. That means that in this NOR gate, our output will also be a 0. And we see that the first property of the SR latch is violated, since Y and X are both 0. If we then run the rest state after the forbidden state, our S will be set to 0 and our R will be set to 0. This means that since this line is 0 and this line is 0, our Y will be a 1. The 1 will then go through this line with this 0 into this NOR gate, and out would come a 0 according to the truth table. The 0 will then go back to this NOR gate, and out would come a 1 as expected. But hang on, we have this state of the circuit since we began computing from this NOR gate. Suppose we were computing from this NOR gate, where Y was equal to 0, X was equal to 0, S is 0 and R is 0 from the forbidden state. If we start computing from this NOR gate, then our X is 1, which would mean if our X is 1, then our Y will have to be 0. So we get different states of the circuit depending on which NOR gate we compute first. This is very problematic because it reduces our reliability for the SR latch. We call it the forbidden state since this state is not to be used. There are many different ways in which you can construct an SR latch. In the example that I showed you, I used 2 NOR gates. You can also use 2 NAND gates to construct an SR latch. Consider doing the following homework exercise to help solidify your understanding of the properties of SR latches. Suppose you have the following SR latch constructed with NAND gates. Then what values must S and R take to store a 1 in X? What values must S and R take to store a 0 in X? What is the rest state for S and R? And finally, what is the forbidden state for S and R?